We talked earlier about different kinds of formulas. We talked about molecular formulas and empirical formulas for compounds. We can calculate the mass percent composition from the chemical formula. We just did that. We can also calculate a formula from the mass percent composition. But it's not the molecular formula. It's an empirical formula. Empirical is a word that means from experiment. So the empirical formula is one that's derived from experiment. It gives us the lowest ratios. So we get the smallest whole number ratio of each type of atom. It's useful, but it doesn't give us the actual number of atoms in the molecule. The molecular formula is always going to be a whole number multiple of the empirical formula. That whole number might be 1. Sometimes the empirical and molecular formula are the same. Sometimes they're not. Let's look at hydrogen peroxide. So the formula for hydrogen peroxide is H2O2. That's the molecular formula. Oops, forgot the 2. Otherwise it's water. H2O2. Is that an empirical formula? No, this is not the lowest ratio. The actual molecule contains 2 hydrogen atoms and 2 oxygen atoms. But the lowest ratio of hydrogen to oxygen is HO, which is what Santa Claus says. Right? So this is the molecular formula, and this is the empirical formula. The empirical formula times 2 is the molecular formula. So the molecular formula is just some multiple of the empirical formula. This is a fancy setup, but you can actually try this at home just by putting a 9-volt battery into a glass of water. Use tap water, though. Not distilled water. And there will be bubbling occur, and you'll have hydrogen gas coming off one of the terminals and oxygen gas coming off the other terminal. In this fancy setup, we've got those terminals captured under inverted test tubes so that we can trap the hydrogen gas and the oxygen gas and then go and weigh it. So a sample of water is decomposed, produces 3 grams of hydrogen and 24 grams of oxygen. How do we get an empirical formula from this information? The formula relates moles of atoms. So we have to get from grams to moles, and then we have to find the simplest ratio. These are the directions. Remembering what to do is the hard part of these calculations. The calculations themselves are not that bad. So I'll read through this and then we'll do an example and hopefully it'll make more sense. You're going to start with the masses of each element. You're going to convert the masses to moles. These are elements. You just grab the molar masses off the periodic table. Not a big deal. We want to get the lowest ratio, so we're going to identify which number of moles is the smallest. And we're going to divide everything by the smallest. At that point, you might end up with whole numbers. Then you do a happy dance and write the formula. If the numbers if the numbers of moles aren't whole numbers, then you have to multiply them to get whole numbers. So this is a table that some of you may find helpful, some of you won't need it. If you have a fractional subscript, if you end up with 2.5, right? 0.5 is the fractional equivalent of 1/2. So if we multiply by 2, we'll get a whole number. 0.33 is a third. We multiply by 3. So you could use the table. The trial and error method actually works pretty well here. If it's not a whole number, multiply by 2. If that doesn't work, try 3. If that doesn't work, try 4. Usually don't have to go past 5. Once you get whole numbers, those whole numbers are the subscripts in your chemical formula. Now, I don't expect that made a whole bunch of sense, so let's do an example. So here's that water example. Here we've got a mass of hydrogen and a mass of oxygen. What we need to do first is convert these masses to moles. So 3.0 grams of hydrogen. We're going to use the molar mass. So we've got moles of hydrogen on top and grams of hydrogen on bottom. We look at the periodic table. 1 mole is 1.008 grams. So I've got 3.0 divided by 1.008. And this is going to be 2.97619. It keeps going a bit longer. You don't have to worry about significant figures when you're doing these calculations. You want to include more digits than fewer. If you round too much, you'll come up with the wrong answer. So write down more. That's why I wrote, this would only have 2 sig figs, but I don't want to round that. So that's what I'm going to call it, and that's moles of hydrogen. Then we have 24 grams of oxygen. 1 mole of oxygen weighs 16 grams. I don't need to remember, do I multiply, do I divide? I let the units tell me what to do. So 24 divided by 16, that comes out to be 1.5. 1.5 moles of oxygen. The next step is to divide both of these numbers by the same number. We want to take the smaller number. This is 2.9, this is 1.5. 1.5 is smaller. The reason we want to divide by the smallest one is so that all of our numbers will be 1 or greater. So if we divide this by 1.5, of course, we're going to get 1. So 1 mole of oxygen. If we divide this by 1.5, let's see, I go up there. Oops. Having an argument with my calculator. If I divide that one by 1.5, I get 1.9841 blah, blah, blah moles of hydrogen. These are not going to come out perfectly because they're based on measurements. So we look at 1.98 and we ask ourselves, well, is that close enough to a whole number that we can round it? And I would say yes. Different people have different guidelines. For the most part, if the difference between the number you're looking at and the whole number is less than 0.2, you can round. So you can round that one. So I'm going to round 1.98 to 2. So 2 moles of hydrogen. So here I have my ratios. These are whole numbers, 2 and 1. And so the 2 is the subscript for the hydrogen, and the 1 is the subscript for the oxygen. This is our empirical formula for water. Any questions? Let's do another example. Sample of a compound is decomposed in the laboratory, produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula of the compound. By the way, this is similar to what we're going to do in lab starting tomorrow, is we're going to find empirical formula of a compound. So Wednesday, people, you're going to need to practice this on your pre-lab assignment. So start with the masses. 165 grams of carbon. I need to convert these into moles. So I want moles of carbon. I'm going to divide by grams of carbon. I get the number off of the periodic table. 165 divided by 12.01. I'm going to write down plenty of digits. This is giving me 13.73 855. That would be moles of carbon. 27.8 grams of hydrogen. I'm going to use the molar mass of hydrogen to find how many moles of hydrogen that is. 1.008 grams of hydrogen. Those, I didn't cancel my units. So 27.8 divided by 1.008. 27.5794 moles of hydrogen. Then I've got 220.2 grams of oxygen. Times 1 mole of oxygen over 16 grams of oxygen. I'm going to get 13.7625 moles of oxygen. Converting mass of an element to moles of an element. We've done that. The new part is we're going to look at these and decide which number is the smallest. Well, it's this one, 13.73. This is 13.76. They're very close, but we need to use the smallest one. I'm going to divide everything by the smallest. By the way, this is not exactly the same as what your book tells you to do. They tell you to take these numbers and write them in as subscripts and then do some dividing. You can do it that way if you want. This is what I like to do. So that first one, any number divided by itself is 1, so that ends up being exactly 1 mole of carbon. 27.57, was that a 7.4 or 9.4? 9.4, thank you. It's a 9. Divided by 7, 13.73855. And this comes out to 2.007 moles of hydrogen. And the one on the bottom, we can tell, is going to be really close to 1. And this comes out to be 1.00 17 moles of oxygen. Is this close enough to 2 that I can round it? Yeah, it is. If I take this number and subtract 2, the difference is less than 0.2. This is also close enough to 1 that I can round it. So I can round this to 2 moles of hydrogen, and I can round this to 1 mole of oxygen. These become the subscripts in my empirical formula. Chemists don't write the number 1 unless they have to, so it becomes CH2O. That's my empirical formula. If you're wondering what order to write those in, just write them in the same order that the book gives you, that the question gives you, and you'll be fine. Any questions? Let's do another one. Ibuprofen. Ibuprofen is my mom answer to anything that hurts. I've got a headache. Take some ibuprofen. I sprained my ankle. Here, have some ibuprofen. It's an aspirin substitute. It has a mass percent composition given here, and we're asked to calculate the empirical formula. They didn't give us the masses. To calculate the empirical formula, we need the masses. Well, What if we decided that our sample size was 100 grams? 75.69% of 100 is 75.69, right? So that's all we do. We just replace the percent with the unit gram. You don't have to understand why you can do that. Those of you that do understand probably got it from that very brief explanation. So just substitute gram for percent and you'll be good. 75.69 grams of carbon. I'm going to go through this one a little faster because we really do need to get on to some other things here. 75.69. So that is 6.3022 moles of carbon. 8.80% becomes 8.80 grams of hydrogen. Whoops, canceled out too much there. Forgot those guys. 8.80 divided by 1.008. 8.737302 moles of hydrogen. 15.51% oxygen becomes 15.51 grams of oxygen. And that is 0.969375 moles of oxygen. Did I do it okay? Did I get the right numbers? I look at these moles, I decide which is the smallest. Well, it's this 0.9. So I'm going to divide everything by that. And that's where I wish I hadn't written so many digits, but I did. That comes out to be 1 mole of oxygen. This one divided by 0.969375. That one comes out to be 9.006 moles of hydrogen. And this one, 969,375, comes out to be 6.5, 501 moles of carbon. One of them is always going to be exactly 1. Can we round this to 9? Yeah, we can. Can we round 6.5 to 7? No. We can't round it to 6 either. This is 0.5 away from the nearest whole number. We can't round it. This is where we need to multiply to get a whole number. So, trial and error method says multiply by 2. So take that number in your calculator and multiply by 2. What do you get? 13.002. Is that close enough to round to 13? Yeah, it is. So we're going to call that 13. If we don't multiply the other ones by 2 also, then we'll have changed the ratio. We have to be fair. If you multiply the carbon by 2, you have to multiply the hydrogen by 2 and the oxygen by 2. So this one times 2 is going to give us 18, and this one times 2 is going to give us 2. So those are our numbers. The carbon has a subscript of 13, the hydrogen has a subscript of 18, and the oxygen has a subscript of 2. Those numbers may seem a little big, but ibuprofen's a big molecule. Any questions? Yeah. I multiplied by 2 because 6.5 is not close enough to a whole number that I can round it. If you express that as a fraction, 6.5 is 13 halves. Right? You can do that on your calculator. 13 divided by 2 will give you 6.5. If I multiply that by 2, then I get a whole number instead of a fraction. If you multiply by 2 and you get something like, 13.7, well, you still can't round it. Go back to the original number, try 3. If that doesn't work, go back to the original number and try 4. And, try 5. If that still doesn't work, text me and I'll help you figure it out. Yes?
So let's say you have to multiply by 4 and you do it for each of them?
Yes, if you have to multiply the problematic one by 4, you have to multiply all of them by 4. Because this is the ratio. It's 6.3022 to 8.7302 to 0.969375. But that makes a really messy formula. This is our technique to convert those into whole numbers.
What if you multiply it by a factor and you make one of them a whole number, but then you mess up another one? Will there ever be a case like that?
That should not happen, no. If you multiply one to fix it, you shouldn't mess up another one. If that seems to be happening, you might have done a calculation wrong. Because all compounds have whole atoms in them. And so it has to have a small whole number ratio of atoms. Any other questions? You guys woke up. It's good. Here's a slightly different one. This is very similar to what we're going to do in lab. A 1.56 gram sample of copper reacts with oxygen to form 1.95 grams of the metal oxide. What's the formula of the metal oxide? They're not just handing us masses or percentages on a platter. This is more like the data you're going to get in lab. Well, what is this stuff here? Let's write a very simple equation just describing what happens, just using words. So we've got copper, we've got copper reacting with oxygen. In Chapter 7, we're going to learn how to write chemical formulas. But for now, we're just going to do this. Copper plus oxygen is going to make this metal oxide. It's some sort of copper. We don't know what its formula is. Some sort of copper oxide. Okay, I'm just describing in a more simple way what that sentence is telling me. Well, they're giving us the mass of the copper. So I've got 1.95 grams of copper, and this is the mass of the product, the metal oxide. So that's what's being made, 1.95 grams of that. Maybe you're not awake. Maybe I'm not awake. That's wrong. I can't read. 1.56. 1.56 grams of copper. So how do you have 1.56 grams of copper and then you end up with more products? You add oxygen. Oxygen is coming into this and being combined and trapped in the compound. What's the mass of the oxygen? It's the difference. That mass plus this mass has to equal the final mass. So the mass of the oxygen is 1.95 minus 1.56. 1.95 minus 1.56. Well, I can't even do that right. I ended up with minus 154. That's not possible. I missed a decimal point. 0.39. So it has to be reacting with 0.39 grams of oxygen. This is one of those types of problems that you can do no problem if you think about bowling balls in a box or something that you can visualize in real life. When we talk about masses of chemicals, your brain goes haywire and you forget how to think. If I had a box that weighed 1 pound and I put some bowling balls in it and now it weighs 15 pounds, what's the mass of bowling balls that I put in the box? It's the difference, right? That makes sense. That's all we're doing here. We're taking copper, we're adding some unknown mass of oxygen, we know what the total is, and so we just subtract. Okay, enough blithering. Now we have our masses, we just do the same thing that we've been doing before. Not 9.5. The 9.5 doesn't come in at all anymore. 1.56 grams of copper. So we have to convert to moles of copper. 63.55. So grams of copper cancel out. 1.56 divided by 63.55. So we get 0.02455. It should have 3 sig figs. You need to make, I should probably do more than that. You want to carry some extras so you don't end up with rounding errors. Because all the significant figures go away in the end anyway. 0.339 grams of oxygen. This is where the 16 comes in. 1 mole of oxygen weighs 16 grams.
Where did you get that 63.55?
From the periodic table. 1 mole of copper weighs 63.55 grams. 0.39 divided by 16. Syntax error. It only wants 1 division sign. Crazy thing. 0.024375 moles of oxygen. This is the smallest. I'm going to divide both of them by the smallest. This one ends up being 1. Divide this one. Yeah, I don't need that. 0.0245476 divided by 0.024375. That comes out to be 1.007. Can I round that to 1? Yeah. So my formula is CuO. 1 of each. Any questions?